We do have exam 1 coming up on Wednesday. So again, we will have a short lecture at the beginning, and then we will take the exam during lab time and stuff like that. All right, so this is chapter 4, which is elements, atoms, and ions. So first thing to talk about is formulas for compounds. And as we talked about a couple of times, or I think a number of times earlier on, a compound, right, is a little bit different in a sense than, or there is a difference, as we talked about, between a compound and a molecule. They can be the same, but a reminder that a molecule, again, is just a more general definition. Basically, you just have two or more atoms together in a particular case, which would be a molecule. Those atoms can be the same element, which will still make it an element, but it's still a molecule like H2. But again, a compound is different because it does need to be atoms of two different elements together. So you do need those two different elements coming together to make a compound. So water, for example, always has two hydrogens and one oxygen. And again, water, which is H2O, is both a compound and a molecule because it does have obviously two or more atoms together, and it's a compound because it has two or more elements involved as well. And again, water obviously is not an element, as we probably talked about, but again, that again is the difference between a compound and a molecule. Once again, they're a molecule, basically just two or more atoms together. So those can be elements like our diatomic molecules, H2, O2, N2, Cl2, and so forth. We represent, obviously, a compound with a chemical formula. And the chemical formula uses the symbols that can be found on the periodic table. And as we can see, most symbols are either one letter or they are two letters. And again, typically speaking, if it is a one-letter symbol, it is always capitalized, like capital K for potassium. If it is a two-letter symbol, first one is capitalized, second one is not, like Na, which is sodium. The reason it's important to do that is if you write something like CO and C capital O, capital C lowercase o is cobalt, which is an element. Capital C and capital O is carbon monoxide, which is not an element. So they're two very different things. So always when we write symbols, first letter capitalized, second one not. If it is a two-letter symbol, carbon monoxide would be both a molecule and a compound, as it has obviously two different elements involved in that particular case. So we represent the symbols with the elements with their symbols. We also use a subscript to indicate how many of each of those there are. So when we do look at something like H2O, the 2 goes to the guide to the left. And again, if there's nothing written, it is assumed to be 1. And again, it always goes to the guide to the left there when we look at it. So in the case of carbon monoxide here, we would have 1 carbon and we would have 1 oxygen in that particular formula. Any questions on that there? All right, so as we talked about there, each atom represented by a symbol. We use the subscripts, and we do not write 1, which is a very common sort of theme in chemistry. Pretty much if we don't see something there, it's assumed to be 1, not 0 in most cases, is what we see. So here we would have 1 carbon and 2 oxygens. This would have 1 nitrogen and 3 hydrogens here in this particular case. And obviously the water there that we saw has our 2 hydrogens and our 1 oxygen. All right, so let's take a look at each of these. We're looking for a molecule that contains 6 carbon atoms and 6 hydrogen atoms. So why don't you write the formulas for each of these, listing the elements in the order they're given. See what you come up with. Okay, let's take a look and see here. So we're looking for a molecule that contains 6 carbon atoms. So that would be C6. and 6 hydrogen atoms, which would be H6 there. So C6H6 would be our formula. A compound that has half as many calciums as there are chlorines. So if I just had 1 calcium, that would be half as many chlorines, which would mean I need 2 chlorines in that case. So CaCl2. And lastly here, a compound that contains equal numbers of sodium and nitrogen. So might as well just start with 1 of each. And 3 times as many oxygens. So O3. Any questions on those formulas there? Okay. Okay, so the next thing we're going to talk about is really the atom, and we're going to talk about some experiments that led to the understanding of the atom and some parts of the atom. And as we go through it, we'll kind of point out what you definitely should know. So when we talk about the atom, everything started a long time ago with a lot of philosophers that really thought that matter was really composed of these really small, indestructible type of particles that they called atomos. And obviously that is a forerunner to what we call atoms. Most natural materials are composed of pure substances, and pure substances are either elements or compounds. And one of the early sort of laws, the law of composition, says that basically a given type of compound always contains the same composition regardless of where it comes from. So 8 grams of oxygen and 1 gram of hydrogen in water, and that is because water is H2O, and that's about 2 grams of hydrogen for every 16 grams of oxygen, which if you reduce down gives you about 1 gram of hydrogen for every 8 grams of oxygen that you have in this particular case. And that's regardless of where you get, basically where you get your water from. It should always have that composition, even if it costs more, no matter how it's bottled. If it's just the water part, it's always the 1 gram of hydrogen per 8 grams of oxygen. And that goes really for anything. And really what was found a lot of times was that atoms really come together in that sort of ratio of so many grams for so many grams of another element. So really in this, what we're saying is for every basically 1 gram of hydrogen, we should have basically 8 grams of oxygen that's happening in that case. And that leads us to one of the first sort of important theories that was done by John Dalton. And Dalton was an interesting guy. He kept weather reports every day of his life, kind of wrote the weather down. He never married, but he did like to go bowling on Thursdays, which is clearly, if you learn nothing else in this class, that is exactly what you should know for sure. That will be on the exam, every exam. So don't miss it. Don't say Friday. Don't say Sunday. Make sure you say Thursday. But really what he came about was really a precise definition of really what we call atoms. So let's take a look at some of the parts here of Dalton's atomic theory. And because it is a theory, as we talked about earlier, theories, again, are things that may be found not to be correct in all aspects. And that's true for Dalton's atomic theory as well. There are sort of a couple of parts of it that are not necessarily true, but there are parts that obviously do sort of work. So he said that basically these elements are composed of these extremely small particles that are atoms, and they're sort of indestructible. And he said that basically all atoms of a given element are identical, and they have the same size, the same mass, and chemical properties. And he said atoms of different elements are different than those. And these are a couple of things that are sort of incorrect. Atoms of different elements are incorrect because there's the existence of what are known as isotopes. And isotopes are basically the same element, but they have different masses. So obviously, if they are the same element and they have different masses, their atoms are not identical because they have different masses. Otherwise, they would have the same mass. So the existence of isotopes is one thing that makes Dalton's atomic theory, part of it here, incorrect. Also, the atoms being indestructible is also another aspect that's incorrect. Nuclear chemistry or nuclear reactions, you could basically change one element into another, but under chemical reactions, it doesn't change. So those two parts of it are not so correct. The rest of it is still correct today. So this part of it here having, I'm sorry, not that one, this part right there. Atoms of different elements are different from each other. So an atom of iron is different than what you would see in an atom of carbon or copper. Compounds are composed of atoms of more than one element. So as we've been talking about, you do need two or more elements to be involved to have a compound. A chemical reaction involves really the separation and sort of recombination of all the atoms. And that is true. That is what happens in a chemical reaction. Again, the only thing that happens in a chemical reaction is that we break all the bonds on the reactant side, which is our starting material, and we make all the bonds on our product side. And we do not do anything really to change the elements. So that's why in a chemical reaction or a chemical equation, when we balance it, if we started with 6 carbons on the left-hand side of the arrow, we should end with 6 carbons on the right-hand side of the arrow. We don't create or destroy any elements along the way. We really do have conservation of the elements. And that is different than what happens in a nuclear reaction. If you go to 1B, you'll have a whole chapter on nuclear chemistry, but in a nuclear reaction, you do nothing but basically change the elements into different elements along the way. So in a normal chemical reaction like we deal with here, that is true. All we do basically is break bonds and make bonds on the other side. So that brings us to the law of conservation of mass, which basically states matter cannot be created nor destroyed. And that really does tie into what we were just talking about. Again, because we do not really change elements from sort of starting to ending, although they may be in different sort of orientations at the end. If we started with 6 carbons, we have each carbon has a mass of 12 grams, and we end with 6 carbons. They also have a mass of 12 grams. So the mass at the beginning and the end will be the same. Again, they just may be in different sort of compounds from where they started from. Any questions? Yeah. They are indestructible in a sense because they're not really, there's nothing really happening to affect that would sort of destroy an atom and make it into something else. So as we'll talk about, pretty much we have our nucleus, and then we have our electrons on the outside basically of the atom. So what really determines what the atom is everything inside the nucleus. And in a normal chemical reaction, the only thing that participates basically are the electrons on the outside, which have really no bearing on what element it is. So in a normal chemical reaction, all we're doing is playing with the electrons, breaking those bonds and making new bonds. The core of what those elements are basically remain the same. And that's totally different than what happens in a nuclear reaction, which we don't talk about in this class, but in 1B you do. In a nuclear reaction, you're doing nothing but changing what happens in the nucleus, those particles, which are really important for what makes an atom an atom. Other questions? All right, so obviously you should know the different parts of Dalton's atomic theory. You should know the couple of things that are not correct still. So again, atoms being indestructible is not correct. And also the main one, atoms are not identical for the same element because of the existence of isotopes, which have, again, basically different masses. This is also how Dalton pictured compounds as a collection of atoms. And again, there's always sort of the same ratio in terms of mass of one element to the next. So for example, there's always sort of a whole number ratio of what's present. So for example, if we look at this, this is nitrogen, which is about 14 grams, oxygen, which is about 16 grams. And basically, if you figure out the grams of nitrogen to the grams of oxygen in this case, we basically take 16 divided by 14.01. And that gives us basically 1.1, we'll call it 4. For every 1 gram of nitrogen, there is 1.14 grams of oxygen. So if we come over here, that is nitrogen, which is our 14 grams. That is 2 times our 16, as there's 2 oxygens, which is 32 grams of oxygen. So again, if we took our oxygen divided by our grams of our nitrogen in this case, we'll end up with roughly 2.28 grams of oxygen for every 1 gram of nitrogen in this case. And that is sort of what we would expect in this case. For every 1 gram of nitrogen, there's 1.14 grams here of nitrogen. And in this case here, we have basically that same ratio. There's twice as much oxygen as we would expect in this case. So basically, since we have 2 oxygens, we should expect 2 times 1.14 is 2.28 as we get on that side. So for every that, we do expect to see that ratio that's sort of happening in terms of how many grams of oxygen per nitrogen. So they always sort of come in these same ratios regardless of the compounds. Any questions on that there? All right, so let's talk a little bit about the structure of the atom. So a couple of things were sort of thought about based off of Dalton's atomic theory here. And that was the idea that atoms are really the basic unit of each element that can enter into chemical combination. A lot of experiments were done, and it was found that basically atoms are really small. And even though they are really small, they do still contain an internal structure of even smaller particles. And these are our subatomic particles. And our subatomic particles are electrons, protons, and neutrons. And as you may know, and as we'll talk about as we go through this, electrons have a negative charge. Protons there have a positive charge. And neutrons have no charge in this case. So we're going to talk about a number of, again, experiments that helped us understand sort of each of these particles, or led to an understanding of each of these particles, and to overall how the atom is sort of put together and where we find sort of all these guys. So the first thing that we really will focus in on is the electron and some of the important experiments that happened with that. And one of the biggest sort of help to the discovery of the electrons was really the idea of the cathode ray tube, which is the CRT. And in chemistry, there's this basic idea of opposites attract. So things that have a positive charge and a negative charge are attracted to each other. And it's much like in life. Again, if you get, 2 people that are quite negative near each other, they really don't want to be near each other, so they repel each other. You get 2 positive people, that's like way too much happiness, right, in one situation, so they're not going to really be near each other. So opposites attract, right? And things that have the same type of charge repel one another. So things that are negative and negative are positive and positive. They really do not want to be near each other. Those opposites, guys, really do sort of attract one another. And by the way, the strength of that positive negative charge is affected by the actual sort of number or value of the charge. So if you have something that is +1 and -1, it's going to be attracted to each other. But if you have something that's, say, +3 and -3, it's also going to be attracted to each other, but much stronger. So as the charges increase, that positive negative attraction will be stronger between them. So this is sort of a picture of a cathode ray tube. And a cathode ray tube basically shoots negatively charged particles, like electrons. And it usually will have a charged plate on it. So it'll have a positive side and a negative side to the plate. And again, that opposite attraction there, those negatively charged particles are going to be attracted to the positive side there of that electrical field. So they would head down towards that part. A lot of times they'll put something at this end, or you can kind of see where they're hitting. It'll kind of fluoresce. They obviously will go away from the negative side of the sort of cathode ray tube. You may be familiar with cathode ray tubes if you've seen an older TV that has like a back on it and stuff like that. Nothing flat like this. Our old computer monitors, they were kind of big back of it. Those are our CRT tubes. It's like your picture tube in your TV. Years ago, you didn't just, go to Costco and buy a new one. You call the TV repairman out, who'd open up the back of the TV and like fix your picture tube, which was in there. So anything that has sort of a big back on it used to be like CRT monitors and stuff like that. So maybe you've seen them around or not. But again, as I mentioned, what happens is we have these negatively charged particles attracted to the positive side of that electrical field, and that's our cathode rays, those negatively charged particles. Again, they will a lot of times sort of coat the surface, so you can kind of see where those beams are hitting. They'll sort of fluoresce as they sort of hit the end of it. This brings us to an important idea again about sort of the opposite attract type of thing. In these experiments where we are studying sort of the nature of the atom, they really use this idea of opposites attract to their benefit, and they're able to do that by using something like electrical fields or even a magnetic field, which has a North Pole and South Pole, which sort of works similar to an electrical field. And if we were to shoot a beam at it, an electrical field, and for example, there's really sort of 3 types of radioactive particles that were used a lot in these experiments throughout sort of the discovery of the atom. There's alpha particles, which are positively charged radioactive particles. They are beta particles as well, which are negatively charged sort of particles. And there's actually gamma rays, which are basically have no charge. So these 3 sort of radioactive particles were used a lot in a lot of different experiments to help investigate basically the atom. And we could use sort of these electrical fields to our advantage to help us understand what's going on. So as you can kind of see here, and as we talked about a second ago, they're sort of equivalent to our 3 subatomic particles in a sense. Like we have our positive guys, which are like protons. We have our negative guys, which are like electrons, and we have our gamma rays, which are kind of like neutrons in a sense of how they sort of interact. So if we have, like this picture shows, a electrical field here, and we shoot a particle at it and it bends towards the positive part of the electrical field, we can make a pretty good assumption that that particle has what type of charge? It would have a negative charge, right? As it's going to be attracted towards that positive side of the electrical field. If we shoot a particle and it sort of bends towards the negative side of the electrical field, we also can make a good assumption that that is positively charged, right? As it's going to be sort of attracted towards it. And also if we shoot a particle and it just sails right through with no problem, that would mean it probably has no charge, as it would be unaffected by both really the magnetic field and the electrical field in this case. So again, a lot of these experiments, including sort of the cathode ray tube, took advantage of this sort of property to help investigate these different types of particles. Any questions on that there? So this is a cathode ray tube. Think of
a cathode ray or Crookes tube. It produces a beam of electrons, as do television sets and computer monitors. A luminescent material has been painted on part of the inner surface of the tube. It produces light when electrons strike it. The electrons originate at the cathode of the tube. The long, thin object entering the scene is a bar magnet. The position of the bright spot on the screen can be changed by moving the magnet near the beam of electrons. This process is analogous to adjusting a television picture.
So you can see that little light there is your beam of negatively charged electrons. And again, as you can see by moving the magnet around, it's affected because it has a charge. And this is basically what a cathode ray tube looks like. Any questions on that there? All right, so one of the major sort of experiments that came out for electrons using this cathode ray tube was done by a guy named Thomson. There he is staring at his cathode ray tube. And he did a lot of work with the cathode ray tube. And basically what he was able to determine out of his use of the cathode ray tube was the electrical charge to mass of an electron. So he was able to figure out basically the charge to mass of an electron. And he found that it was negative 1.76 times 10 to the 8, capital C, which is a coulomb. So that's a unit of electrical charge. So that's the charge over grams, which is G. So charge to mass of an electron. So this was really a first step towards an understanding of really the charge and also the mass of an electron was this work that was done by Thomson. It was really followed up by another important experiment that helped us understand a little bit more about electrons, which was one that was done by Millikan. And Millikan did what is referred to as the oil drop experiment. And essentially what he was able to do was he was able to use a chamber such as this. And basically he shot oil droplets into here. And he was able to use this electrical field basically within the chamber. And he was able to adjust it in such a way that basically that drop kind of just hung there. Because as it was coming through the chamber and dropping, it would gain sort of a charge, right, as it's moving. And he was able to really adjust the electric field in such a way that he was able to have the electrical or the oil droplet basically just remain there. And I think maybe that will do it. I think. There we go. So that was his experiment. As you can see, he's able to adjust the field so that the oil droplet there on the left just really just sort of hangs there. And from that, the really important information that he was able to get from that was the charge on an electron. So Millikan in his oil drop experiment was able to use, again, that electrical field and the charge of electrons to his advantage to figure out the charge of an electron. And that's minus 1.6 times 10 to the minus 19. So the importance of these two experiments together was, if we think about it, we have our Millikan that figured out the charge of an electron. We had our Thomson that had the charge to mass of an electron. And basically, we could use both of these pieces of information. And if we kind of divide it the other way, where we take the charge of an electron divided by the charge to mass of an electron, they were able to basically put together the mass of an electron by using the results of these two experiments. As one, again, had the charge to mass and one had the mass, the charge of an electron. So doing that and putting those sort of calculations together, we get the mass of an electron, which is 9.09 times 10 to the minus 28 grams. Any questions on that? So to summarize these first couple of important experiments for our electron, we have Thomson in his cathode ray tube that was able to figure out the charge to mass of an electron, followed by Millikan in his oil drop experiment that was able to basically determine the charge of an electron. Again, putting both of those experiments together allows us to get an understanding as to what the mass of an electron is. By the way, is that a large or small number? It's a really small number, right? We're going about 28 places to the left and putting zeros, right? But this is the mass of an electron. Probably a good number to sort of know. Might pop up along the way. Yeah. Right. Yeah. He wasn't able to determine just the charge, but just sort of the ratio of those two. And really, it was sort of confirmed more what the charge aspect of it was from Millikan's experiment, and then it kind of put them together, able to figure out the mass component of it. Other questions? All right, so this was an important step, obviously, to an understanding of atoms. We now have an understanding of our negatively charged electrons, sort of the mass of it. And this led to some other features of the atom sort of being discovered or sort of being looked at. And it was always thought that there's really two parts to the atom in a sense. Obviously, they contained electrons through these early experiments, and they were electrically neutral. So obviously, if they do contain electrons which are negative, there has to be something that is positively charged in the atom to allow it to be neutral, right? It's the only way you can get something neutral is to have equal numbers of positive and negatives, right? Kind of cancel each other out if you do have something with charges. So around the turn of the last century, the accepted model for the atom was the one that was proposed by Thomson. And this model of the atom is sometimes referred to as the plum pudding model. And his idea of the atom was that basically the atom is this sphere of positive charge. So it's just a sphere of positive charge. And he felt that embedded inside the atom were all these electrons. And he also felt that most of the mass of the atom was actually those electrons. So he felt that most of the mass of the atom was those electrons. And we have this really positive charge kind of distributed out over the whole sphere of the atom, really diffused. This is what is referred to as the plum pudding model, and that's a dessert that's like pudding and raisins. So he thought like the pudding was like the positive charge smeared out over, and the raisins were like the electrons that were basically dropped in there into the atom. And this was really sort of the accepted model of the atom. Here's a much prettier picture of that. Again, our positive charge spread out all over it, our electrons embedded inside, with it being the most of the mass of the atom. And this, again, as I mentioned, was a sort of accepted model of the atom until, again, further sort of experiments were performed. And the next really major experiment that was performed that helped us, in a sense, move away from this sort of model was one that was performed by Rutherford and some other guys like Geiger and Marston. But Ernest Rutherford did the popular gold foil experiment. And basically what he did is he used pieces of gold foil and other metals, and he basically shot these alpha particles at him. So as I mentioned a second ago, and as we saw, he used these alpha particles, which again are radioactive, positively charged particles. They're really helium, nucleus basically. And he shot these alpha particles at basically these pieces of gold foil. And he had an expectation based on sort of the plum pudding model that, you know, we're going to take these alpha particles, which are positively charged. We're going to shoot it at this atom that has really all this positive charge spread out through it. So what he anticipated to happen is actually different than what he actually did happen. And that is because if you just think about it, if this was like my atom here, that's now a paper size and shape, and this was my positive charge really just spread out all over it. And if I held like one side of the paper, somebody else held the other side, and we shot this pin at it, right? And it was moving really, really fast, it would probably be able to punch through and then kind of come through, but there probably would be some deflection, right, as it tried to went through, but it would be able to probably really punch through as we have this really spread out positive charge, and this was moving really fast, it would be able to punch through. So what he thought would happen is, as he shot these things, he thought they would go through. And since it's sort of positive at positive, thought there would be some deflection because, again, that repelling of those charges are the same. But they are moving really fast or heavy. So, you know, it would be able to sort of punch through, but a little bit of resistance as it sort of punched through the atom. And actually what he saw when he did this experiment was just really surprising, as we'll see here. So what he saw, as we saw in that video, is most of them basically went through with no problem. So they just kind of sailed right through. But every so often he did, as you can see in that animation and also on this picture here, did have alpha particles really bouncing off at these really, really large angles. So this was really surprising to him based on sort of the plum pudding model, because he thought, most of them should hit something that's positive as it's going through, and we should see some deflection because of the positive and positive. So clearly he had to sort of rethink about the model of the atom based on his results. And based on his results, he found again that, most of them sailed through with no problem, which means they pretty much hit nothing, right? And take my pen example, my paper's out of the way and I just throw my pen, right? It's just going to sail through no problem, right? It's because it's not going to hit anything, right? There's nothing in its way. And that's basically why they saw most of the alpha particles sail through with really no problem. Now, every now and then, as they saw these alpha particles being scattered at these really large angles, in order to scatter these alpha particles at these really large angles, since alpha particles are positively charged, it had to hit something that was really, really densely positively charged to make it do that, right? So it had to run into something that was pretty densely positive charged. So if we go back to my example here, and instead of this being the atom with all the positive charge spread out all over the entire atom, if we take our positive charge, just like you could do and fold it right here, and if I fold my positive charge down, what do they say, like 7 times you can fold a piece of paper before you can't really fold it anymore. All right. So now if I take my positive charge, instead of being spread out all over, and now it's really just confined, really to this, and I shoot my pen at it, right? We can see that it's not going to go through at all. It's going to hit something really massively singular charge and be positively bounced off at those really large angles. At least it went that way. I guess that's good. So with all this sort of knowledge that came out of Rutherford's experiment, what he expected to see was on the left here, going to be able to punch through, but what he actually saw here again is on the right. They really had to go and pretty much say, not so good, the plum pudding model. We have to sort of move away from the plum pudding model. It's not a really accurate representation of what's happening here in the atom, and really come up with a new model of the atom. And basically Rutherford's idea of the atom was that the atom is mostly empty space. So basically the atom is mostly empty space, which accounts for, again, why those alpha particles really did not have any problem flying through, didn't deflect or anything like that, because frankly, it didn't hit anything. He also explained that there had to be a really dense positive core, which is the nucleus. So we have this positive nucleus here. And as later experiments would find, that is where we have our protons, which are positively charged, which makes sense. Also in like the 1930s, it was found it also has neutrons in it. And out and about, really from the nucleus in that empty space, is where our electrons are basically flying around. And do our electrons travel in pretty little circles? They do not, actually. They travel randomly about the nucleus. We'll talk about in a later chapter. They actually don't travel in pretty little orbits or anything like that. They do travel randomly about the nucleus in this empty space, which is sometimes referred to as the electron cloud around the nucleus, right? Or that empty space of where they're traveling. Is there an attraction between the electrons and the nucleus, though? There is, right? Because the nucleus is positively charged. Electrons are negatively charged. So although they are flying around in that empty space, there is still some attraction between the nucleus and the electron. And it's also, as we'll talk about in other chapters, the basis as to why certain electrons are involved in bonding and other ones are not. And it depends sort of on their location of how close they are to that nucleus. They're going to feel a much stronger charge if they're closer to the nucleus and can be held tighter than if they are an electron further away from the nucleus flying around. They will still feel an attraction to the nucleus, but not going to be held as tightly. And those further electrons, as we'll talk about, which are valence electrons, are really the ones involved in bonding because of that reason. They're not held as tightly. They're furthest away from the nucleus. They are pretty much on the outside when two atoms come together and come in contact with each other. Any questions on that there? The other major difference as well between the plum pudding model and really the modern version of the atom is the idea that most of the mass of the atom is the nucleus. So remember, in the plum pudding model, his idea was most of the mass of the atom is actually the electrons, but the actual truth is most of the mass of the atom is actually made up of what's in the nucleus, which is really, as we'll see here, protons and neutrons are really the most massive of those guys. Any questions on that? So you need to know Thomson's model, plum pudding model, what it was, yes. You know the idea of what Rutherford did with the alpha particles in the experiment, what he thought would happen, what actually happened, and obviously the revision to our modern version here of the atom, mostly empty space, nucleus positively charged, most of the mass of the atom is the nucleus. Any questions on any of that? So here's just a table of some of the experiments that we talked about, and again, sort of what came out of those experiments. Just a nice little summary table of, you know, everything that we just talked about, and kind of what you do need to know pretty much. Now, obviously, as we've been talking about this idea that the nucleus contains our protons, which are positively charged, it was determined that the mass of a proton is 1.67252 times 10 to minus 24. If you remember the mass of an electron, 909 times 10 to the minus 28 grams. The one that's a larger number is the proton, yes. Something to the minus 24 is a larger number than to the minus 28. Sometimes people mess that up because there's the negative part there that's important. Minus 24 means I'm only going 24 places to the left and putting zeros. Minus 28 means I'm going 28 places to the left and putting zeros, which is more zeros, so it makes it a smaller number. So when you have a negative exponent, the smaller number is the larger number when you are comparing those two. So our proton here is about 1,840 times heavier than any electron. That also puts sort of credit into Rutherford's idea that most of the mass of the atom is the nucleus, because that is where we find our protons in the nucleus. And each proton that's in the nucleus is about 1,800 times or so heavier than any electron that's flying around in that empty space. So at this stage, basically people perceive the atom as, although the atom is really small, the nucleus comprises most of the mass of the atom, but it's really a small volume of the actual atom. So you can think about it like the atom is the size of the Superdome or some big football stadium. If you've never been to the Superdome in New Orleans, it's a big football stadium. You sit in your seats, you feel like you're falling over when you're sitting, and it's so pitched that way. But it's like a big football stadium is the atom, and like on the 50-yard line in the middle, a little marble there is like our nucleus. So again, although it does have most of the mass of the atom, most of the volume of the atom is empty space where we have those electrons flying around. And again, this is what leads to what we saw with Rutherford's experiment, that most of those particles just sailed through no problem because it was aiming to be able to scatter, had hit a really, really small part of it. That's, although it's really small, very dense, but that's why we didn't have those big deflections happening all the time. Now, the neutron, which is our third subatomic particle, there was always a belief that they did contain another sort of particle in the nucleus. And it was actually not until about 1932 that the discovery of the third particle was done by Chadwick. He did a lot of work with sheets of beryllium, with alpha particles. And what he saw was it emitted radiation that was very similar to our gamma rays. And if you remember, our gamma rays, as we talked about earlier, are guys that have no charge. So by sort of exploring this, he was able to sort of see these particles come off. They were very similar to gamma rays that have no charge. So obviously they associated no charge with our neutrons. And experiments found that the mass of a neutron was 1.675 495 times 10 to the minus 24. That is, if you look at the mass of a proton, it's just slightly heavier. And that's why they take it out to so many digits there. The other one is roughly about the same, but it is actually our neutron that is the heaviest of the 3 subatomic particles. So our neutron also is about 1,800 or so times heavier than an electron. And he called these guys neutrons. So in terms of our 3 particles, our protons, electrons, and our neutrons, it is the neutron that is the heaviest, just barely, followed very closely by the proton. And again, it is the electron that is the lightest of those 3 subatomic particles. So if the neutrons are also found with our protons inside the nucleus, once again, this does sort of back up Rutherford's idea that most of the mass of the atom is that nucleus, because in the nucleus we have both protons and neutrons, and each of them individually are about 1,800 times heavier than any electron flying around. So again, that's going to be where most of the mass of the atom is basically concentrated. Any questions on that? So here's just a table of our 3 subatomic particles. Once again, positively charged nucleus, where we find that. Electrons negatively charged in that empty space. Our electron cloud. And no charge here for our neutron in our nucleus. And as you can see, very, very close, these two. But the neutron just barely, if you take it out to 32 decimal places or so, a couple of decimal places past each other, we do see our neutron being the heaviest. So here's sort of a idea of what an atom looks like. This sort of reddish color here is the empty space or electron cloud. You can kind of see the difference up there. And our idea here is our nucleus, which once again is positively charged there in the middle. So again, this is what is sometimes referred to as an electron density map. The darker color is a higher probability of finding an electron. The lighter color is a less of a probability of finding an electron. And as we talked about, and we'll talk about more, we really don't know how they're moving or where they're exactly located. That is what is sometimes referred to as Heisenberg's uncertainty principle. Best we could do is make a good prediction of there's a pretty high probability of finding an electron in a particular spot within the atom. And as we can see in this map, the darkest area is near the nucleus, which is what we would expect to happen, again, because of that opposite and positive charge between the two things. That's also what sort of ties the electrons to the atom and doesn't allow them to just fly away, right? They're sort of attached in a sense by that attractive force to the nucleus. And again, the further away you get, not as strong of attachment, so they can move around a little bit more and be able to be released. All right. These are the relative masses of each of these guys in relationship to an electron. All right, any questions on the atom? So clearly you need to know those experiments we talked about, what came out of them, the early version of the atom, which is the plum pudding, the current modern version of the atom, which is empty space nucleus. And you need to know which of the 3 subatomic particles are the heaviest and the lightest, you know, that sort of combination. Any questions on that? Okay. Then let's talk a little bit about some other important things about the atom. As we've been mentioning, most of the chemistry really of atoms comes from electrons. As we know from our model here, they're pretty much the ones that are on the outside. When 2 atoms come together, they are the ones that really will come in contact with each other first. And a lot of times it's the difference of their properties are based on sort of what happens when those electrons kind of come together. So let's talk about some important aspects of the atom. That's the atomic number, mass number, and isotope. So we'll start with the atomic number. And the atomic number, which is sometimes abbreviated with a Z, is the number of protons that there are in an atom of an element. Now, if we have a neutral atom, because there's only 3 particles in an atom that we just talked about, which are protons, electrons, and neutrons. And protons are positively charged, electrons are negatively charged, and neutrons obviously have no charge. So if we have a neutral atom, we would have to have an equal number of protons and electrons to balance out the charge to 0. So the atomic number will also tell you, if you are dealing with a neutral atom, the number of electrons you have. There is an important distinction, and it is this: if you are asked a question of what is the definition of an atomic number, the definition of atomic number is only the number of protons. So although in a neutral atom it will tell you how many electrons you have, electrons are not the definition of atomic number. So the straight definition of atomic number is only the number of protons. But sort of the information you can get from that in a neutral situation is also the number of electrons. Any questions on that? By the way, all atoms have protons, electrons, and neutrons except for hydrogen. Hydrogen only has a proton and an electron, does not have a neutron. So everybody else has all 3 of those particles, but hydrogen only has a proton and an electron. No neutrons. Yeah. Now, the chemical identity of an atom can be found by the atomic number. And if you go to the periodic table, we can find the atomic number. It is the number up on top of the symbol. So hydrogen is 1. If we look at nitrogen, it has a 7. And that means that nitrogen would have 7 protons and 7 electrons if it is neutral. Again, to balance out the positive and negative from each other, they would have the same number. If we look at something like calcium, calcium has a 20. That means if I have a neutral calcium ion, it has 20 protons, and it should also have 20 electrons to balance out the charge with each other. If you look at the periodic table and you look at all the numbers that come up on top of the symbols, do any of the numbers repeat? None of the numbers repeat. And that means that every single element has its own unique atomic number, which means it has its own unique protons, number of protons, which is the same thing. You will never find a boron atom with 7 protons, because 7 protons, again, is nitrogen. Boron should have 5 as its atomic number there above it. It will have 5 protons. So this should also tell you, out of protons, electrons, and neutrons, which one is the really most important subatomic particle in determining what element you're dealing with. It is the protons. And so if you know the protons, you know what element you're talking about. All you need is a periodic table. That is also why we were talking about earlier that in a chemical reaction, it's only electrons involved. So because the protons, which are in the nucleus, never change in a chemical reaction, that's why we have the same elements that we start with and end with, because we'd never touch the protons. And in a normal chemical reaction like we deal with in this class, you will always have that conservation of elements. Like I said before, if you go to 1B and you do the nuclear chapter, that is the only thing that happens in a nuclear reaction is pretty much you change protons to neutrons, neutrons to protons. So you keep messing with the nucleus and the particles in there. And that's why in nuclear reactions, there is no conservation of elements. You change something from one to the next element. But in a chemical reaction like we do in here in 1A and these type of things, you never touch what's in the nucleus. So we always have that conservation of those elements, which is why we always need to balance equations when we have equations. So we have the same number of element on each side. Any questions on that? The next important number is the mass number, and the mass number is sometimes abbreviated with an A. And it is the number of neutrons and protons, or protons and neutrons, that you find in an atom. Now, with that together, we have our mass number, which is basically our number of protons plus our number of neutrons. We have our atomic number that we just talked about, which is our number of protons. And if I subtract those two, protons cancel, leaves me the number of neutrons. So if you take the mass number and you subtract it from the atomic number, that will tell you the number of neutrons there are in an atom in that particular element. As I mentioned a second ago, everybody but hydrogen will have all three things: protons, electrons, and neutrons. Once again, hydrogen, just a proton and an electron, which is why hydrogen has some unusual sort of characteristics that we'll talk about as we go through different chapters. When you calculate all these things, the mass number, the atomic number, the number of protons, electrons, neutrons, they all should be positive whole numbers. So they should be positive whole numbers. So that brings us to the important question of, we go to our periodic table and we look at the number on the bottom here. Are these the mass numbers? These are not the mass numbers. These are not mass numbers. The easy way that I know that they are not mass numbers is the very last statement says they all need to be positive whole numbers. And if you look at all the numbers on the bottom of the periodic table, pretty much none of them are whole numbers. They're all decimal type numbers. These are what are referred to as the atomic mass, which we'll talk about in another chapter. And it is different than the mass number. So do not be the person on the test or whatever that, writes the number of like 39.19 or something like that, with a decimal. So if you see yourself writing that number, just put an X, save me a trouble of doing it. And so it should be a whole number. What oftentimes confuses people is a lot of times the mass number and the number that you see up there, which is the atomic mass on the bottom, they're very close to each other. They're very close numbers. So very commonly people will say, is it just like the rounded number of what we see up there? And it's really not. There is a different way that those numbers are calculated, but they're all sort of based on very similarly sort of protons, electrons, and neutrons and the masses. So they do tend to, in certain cases, have very similar numbers, but that's the best way to remember it is they need to be whole numbers. So definitely don't write those numbers because they're not whole numbers. You will have enough information given to you in these type of problems to figure out protons, electrons, neutrons, mass numbers, and atomic numbers. Any questions on that there? All right, so isotopes, for example, as we talked a little about, which is one of the reasons why part of Dalton's atomic theory was incorrect because of the existence of isotopes were found. Isotopes, as I mentioned, are basically the same element, but they have different mass, which means if they are the same element, what cannot change? Protons, electrons, or neutrons? The protons cannot change, right? Because if they are the same element, they got to have the same number of protons. So really what changes and what will affect the mass of it is the other thing that's really the massive particle, which is the neutrons. So isotopes will be the same element, but they will have different numbers of neutrons, which is why they have different masses. Now, hydrogen has one proton and no neutrons. Deuterium, which is sometimes referred to as heavy hydrogen, has one proton and one neutron. Tritium, which is the radioactive version of hydrogen, has one proton and two neutrons in this case. There's a very common way that we write isotopes with the symbol and the mass number and atomic number. So we do use the chemical symbol here for the element. And up on top left is the mass number. Bottom left is the atomic number. So that's a very common way that we write them. So for example, if we were going to write it for each of these, hydrogen, it has one proton and no neutrons. So let's just say, for example, you didn't know what hydrogen's symbol was. You do know it has one proton, which means that is its atomic number. You would go to the periodic table and find number 1, and you would see H standing there at number 1. So you would write H as the correct symbol. You would also put the 1 on the bottom left as that's the atomic number. The mass number would be found by adding these together. So our mass number here would be 1 plus 0, which would be 1, and that would go up on top. And that would be the correct symbol there for hydrogen. if I take the top number, which is the mass number, minus the bottom number, 1 minus 1 is 0. So that's the number of neutrons, right? So top number minus bottom number gives you the number of neutrons. And once again, that is our mass number and our atomic number. Now, if I go to deuterium, which clearly doesn't sound like hydrogen at all, but if you know that it has 1 proton and 1 neutron, it is the 1 proton that I go to the periodic table, and I still see it as number 1 is still hydrogen, which means we should still use the hydrogen symbol, because even though it has a different name, it is still hydrogen because it has 1 proton. If I do my mass number, 1 proton plus 1 neutron gives me 2 for my mass number, which should go up on top. And that would be the correct symbol there for deuterium. We can see it is still, even though it has a different name, because it has 1 proton, it really is still the element hydrogen. And again, if you take the top number, 2 minus 1 gives you 1 for the number of neutrons that are present. And tritium, once again, doesn't sound at all like hydrogen, but when I see the 1 proton, that tells me the atomic number is 1, and that would tell me H. Taking my 1 plus 2 gives me 3 for my mass number, protons and neutrons. And once again, if I take 3 minus 1 gives me my 2 neutrons in that case. So those are 3 isotopes of hydrogen. Although they do have different names, they are all still hydrogen because they all contain 1 proton. So as long as the proton number doesn't change, it's the same element. They all have different masses because each one contains different numbers of neutrons. And again, but they are the same element. Any questions on how to write that there? Another common way sometimes people will write isotopes is do something like this. This is copper, say 64. It's a radioactive version of copper, basically. That 64 right there is what number? Atomic number, mass number? It is the mass number, and that is because I know for sure I could find the atomic number by going to the periodic table, finding copper, and I hope it still says 29 in that case. And above it, it says 29, which is its atomic number. So if we were to write this the other way, copper 29 on the bottom and 64 up on top here, would be the way that we would write the isotope for this. That would mean this copper has number of protons would be how many? 29, which would be the atomic number. In this case, if it's neutral, number of electrons should be 29 as well, right? 29 positives, 29 negatives gives me no charge overall. Number of neutrons in this case would be our mass number minus our atomic number. It's a lot of math there. That's like 35 maybe. I can try it without the calculator, see how I did, hopefully. Any questions on that there? So most of the time, this is probably how you will write your symbols for isotopes with the mass number, atomic number. Occasionally, though, you get into some nuclear chemistry. They sometimes like to kind of write them like that, where you see the kind of the dash and the number. Any questions on that? All right, so why don't we try some here and see how you do, maybe. All right, so for each of these, determine the number of protons, electrons, and neutrons they each have. Take a look. So once again, here we got CO, which is cobalt, and our top number here is our mass number. Our bottom number is our atomic number. So in this case, the number of protons should be equal to our atomic number, which is 27 in this case. This does not have a charge, and I know it doesn't have a charge because when I look over here, that's where a charge would be written. So I don't see anything there. So you can assume that it is neutral. And because it is neutral, that would mean it would need a equal number of negatively charged electrons, right, to basically get to 0 charge and being neutral. Our number of neutrons, once again, is top number minus bottom, or mass number minus atomic number. which should give us 33 in this case. Yeah. Any questions on any of those there? Taking a look at the next one, Cl, which is chlorine. Once again, we do not see anything written there, so we could assume that it is neutral. So our number of protons will equal our atomic number, which is our 17. That means once again here to balance it out, we would need 17 electrons, which would give us no charge when it's all said and done. And our number of neutrons here would be our 37 minus 17. Looks like a 20 in that case. Lastly here, this is uranium. Once again, I do not see anything written there, so we know it's neutral. So we're going to take our number of protons equal to our atomic number, which is 92. Once again, basically, we need an equal number of negatively charged electrons, which will get us basically 0 overall charge. And our number of neutrons going to be our mass number of 238 minus 92. Feels like a lot, like $1.46 maybe or something like that. Yeah, in this case. Any questions on any of those there? All right, let's try a few more here to finish it out maybe for today. All right, so for each of these, write the proper symbol with a mass number and atomic number based on what was given to you. Just see what you come up with. In case you don't have a periodic table near you, that is what it looks like for that guy. Nitrogen looks like that. And iron looks like that. Okay, let's take a look and see. So we'll start with krypton. Clearly, your periodic table is your friend when you're doing this. So we would go to the periodic table, find krypton, which is Kr. Remember, capital first letter, lowercase second letter. From the periodic table, we get some important information, which is 36, which is the atomic number, and that would go bottom left. That's also important because that means the number of protons in this case would be 36 from the atomic number that we get from the periodic table. That's going to be helpful because they did give us a number of neutrons, so we could find the mass number by taking our 48 plus our 36, going to give us 84. And that would go right there up on top. Obviously, in this case, you could assume that it is neutral as it didn't mention anything about a charge or anything like that. Any questions on that one there? Taking a look at the next one, which is nitrogen. Once again, if we roll the periodic table, we find our N there. Once again, the other important information there is our atomic number, which is up on top. So we'll do our N, capital for our 1 symbol here, letter symbol. 7 on the bottom. Again, that 7 is important because that is the number of protons that we have, which is going to allow us to get to our mass number of 7 plus 6, which is 13. There we go on that one there. Any question on those first 2? Lastly here, we're looking at iron. Iron is one of those symbols that you might not think, but it is actually Fe. And once again, we do get our atomic number there, which is 26. Capital letter, lowercase for the second. In this case, they actually gave us the mass number 56, which is what should go up on top. And in this case, we want the protons, electrons, and neutrons. So our number of protons should equal our atomic number. It is neutral here, so we should expect an equal number of negatively charged electrons in this case. And lastly, our number of neutrons going to be our 56 minus 26, going to give us 30 in this case. Any questions on mass numbers, atomic numbers, protons, electrons, neutrons? It's actually, as we'll talk about actually in this chapter, we'll talk probably on Wednesday, but it's actually because this row right here and this row, they actually go after those 2 elements. So if you see LUs at the end of that row, because technically speaking, this row should be right after that element.